everyone. Today, let's work on number 49 in section 7.5. Here, we would like to find all values of P such that the series will converge. Here, P is a parameter, appears in a general term. And the important thing is to break this one into several cases. For example, we would like to distinguish between the negative value of P and the positive. All right. So indeed, these are the four cases that we're going to consider. Less than or equal to 0, between 0 and 1, P equal to 1, P greater than 1. First, we will focus on less than or equal to 0. We're going to utilize the properties k to the power of negative p here. All right. If p is less than or equal to 0, the exponent becomes greater or equal to 0. So that's why we have a lower bound 1. And then this lower bound 1, since it will appear here, and we can establish the upper bound for this term, which is 1 over e to the k. And we can slightly rewrite this term. It turns out that this is a geometric series where r is less than 1. That means we have the convergence for this. All right. So here we could apply the comparison theorem to draw the conclusion. So the original series will actually converge for p less than or equal to 0. Similarly, we discussed the other cases like p between 0 and 1. We could still establish the upper bound, right? P between 0 and 1, and then the kp were less than or equal to k. Then it all depends on the convergence of this particular term. All right. And for example, we could consider to apply the integral test. Indeed, even though this is not in the section 7.5, we could also apply the technique of the ratio test. All right. So the ratio between ak plus 1 and ak, after we simplify it, the limit equal to 1 over e. This is a number between 0 and 1. According to the ratio test result, this means the convergence. All right. Now again, by comparisons test, right? Because this will be the bk in this case. Then the original one will converge for p between 0 and 1. Similarly, we consider p equal to 1, and then it turns out that this is just part of the case 2 there, right? So we will have the convergence state. The last case will be p greater than 1. Here, we can apply slightly different technique. Then we need to choose the bk like in this one, and then consider the ratio between ak and the bk, and evaluate the limit. It turns out that it will be 0. And then according to the results, that means if we can establish the convergence of bk, then ak also convergence. All right. This is actually the case because the bk series is exactly the p series where p greater than 1. All right. And this is actually the setup of the limit comparison theorem. So we can conclude the ak series converge for p greater than 1. Right? A quick recap is no matter what is the p value, we always have the convergence. All right. So we can safely draw a conclusion like this one. Okay. So I will say the most challenging part is to break the p values into several different categories, right? And in each part, we might apply different convergence tests. All right. And indeed, this may not be the only way to decompose the interval, right? You don't have to break this into the 4 cases. You can actually simplify it or rewrite it in another way. But the idea is try our best to localize the range of p, right? Such that we can apply easier technique to justify it. Okay. So indeed, this problem is more challenging, right? And I hope you can understand this. All right, thanks for watching.